this value here would be what?
Negative.
Negative 1.645. Now, if I had an alpha of 0.05, that means how much is in each of these two tails? No. Alpha is 0.5. If I'm splitting it between both tails, how much goes in each tail?
0.1.
No.
Is it half?
Half of alpha,
Oh, yeah.
which would be 0.025. Which means that if it's a two-tailed test, then I have to go out and look those up. And those values would be 0.025. No. 228. 225 would be right here, which is what? 1.96. So this value here would be negative 1.96, and this value here would be 1.96. Those are my table values. What does the alpha represent?
The part correct.
Type 1 error?
It's my willingness to know that I'm rejecting the null hypothesis when the null hypothesis is in fact true. Type 1 error.
Right.
Okay? So see, what I do is, if I do my calculations, if I go out and do my sample data and I collect my data and I do my calculation and I calculate a z value of 1.7. Well, that's out here in the tail, right? So that means I would reject my null hypothesis. If I calculated a negative 1.7, I'd be out here, wouldn't I? But see, that's still in the meat of my table, so I'm not going to reject it. If I calculated, if I was doing this, so that's, it depends on where those values are falling.
Okay, so the alpha is what determines whether.
That's your willingness to make a type 1.
Okay, so
error.
if it said the mean was equal to 6, if the null hypothesis said the mean was
Is
equal to 6, but I had this alpha that they told me what the alpha
Okay,
was.
so we're going to work through it. So if you look at that in-class problem,
Okay,
okay?
I'm there.
Do I have that?
My goodness, my goodness.
So I opened an in-class assignment. This in-class assignment has about 40 problems to it. We're not going to do all of them. I'm going to do some of them. The first one I'm going to do is, say, number 2. So when we first start here, I'm going to start, oh shoot. Here and do this, so that you guys cannot see what's correct and incorrect. How come it's still showing it? Keep taking these off. Okay. So, okay, why are you doing this? I don't want the answers to show. So quit showing me the answers. Hypothesis testing in class. View. Why do you keep coming back?
50,000 from the past studies of this type. Standard deviation is 8,000.
Where is everybody?
They're at Zumba. No, I don't know. There's something going on. The owners of that tire design is conducted of the 31 tires surveyed. The mean lifespan is 36 to 100.
So question number 2. Do you guys have the same numbers on question number 2?
Question number 2.
On the in-class assignment.
I'm there.
That's 1. You're on 1.
I just had it on 2. I had it up there. And I was like,
Particular
what?
brand of tires claims that its deluxe tire averages 50,000 miles. Yep.
And your red number is 46.9 and 9,800?
No.
No, I have
45,
26.
7, and 32.
Huh?
I got 30, 46, 600.
For different numbers.
Damn. I thought I said it so that it would give everybody the same numbers. Okay. The answers are going to basically be the same. You're just going to have to play a little bit with it. So the first question that you have to ask, is this question asking about means or proportions? And this one should be an easy question to answer.
I see the word mean.
You see the word mean.
No proportion.
So it doesn't say proportion. A particular brand of tires claims that its deluxe tires averages at least 50,000 miles before it needs to be replaced. From past studies of this tire, the standard deviation is known to be 8,000 miles. What does that represent?
It's standard deviation of the
Of?
population.
Standard deviation of what?
Population.
Of the population. Fantastic. A survey of owners of that tire is conducted. Of the 31 tires surveyed, the mean lifespan was 46,900. What does that 46,900 represent?
The standard deviation of
No.
the mean.
The mean of
The sample.
the sample of 31
31 tires.
tires.
Yeah.
Okay? Was 46,000, and that sample had a standard deviation of 9,800. So if I'm just going and looking at that, the first thing I want to look at is, this is a mean. Because it said mean. It didn't talk about proportions. It actually said the word mean and talked about standard deviations. So that's what we sort of know. Now, when I'm doing this, now, I do know, will I use a Z table or a T table?
T table says to use. It says if you are using a student's T
If
distribution.
you are using a student T table, you got to give some information. So my first question just said, are you using a Z table or a T table in this problem? Why?
Because it says that we might.
Says you might, it doesn't say you have to.
Personally, I would have used I would have used the normal one.
Why would you use a normal table? There's a reason, there's got to be a reason.
Really? Because the
know why.
population was so big. That's why.
No.
No.
The population is big, but
Yeah.
the sample isn't.
Oh, because it's not proportions.
No.
Because the standard deviation is known.
What standard deviation?
Oh, that's it,
of
right.
The population.
The standard deviation of the population is known. When the standard deviation of the population is known, we use a Z
Z table.
table. See, this is why I say it's important to be able to identify everything. So I'm going to look at this, and since the standard deviation of the population is known, I'm going to use a z-table.
Okay.
So when it's not going to use a T-table?
When the standard deviation of the population is not known, I use a t-table. So see, that's the first part. So now I have to go back. What's my n?
30. Oh, yours is 31.
Mine is 31. What is my sample mean?
$46,900.
46,900. What is the sample deviation? The sample, a sample of 31 people, of 31 tires
Oh,
was taken
9,000.
with a standard deviation of 9,800, but we had the population deviation known of 8,000. See this, so all I have, all I'm looking at now, what type of test? Means. Okay? Now I'm going to look at it, and the next first thing I want to know, and I'm going to have to sit down and do this because I didn't leave room for it. Insert. My null hypothesis would be what?
That's a good question.
So looking at the question, it
A
says,
particular brand of tires.
a particular brand of tires claims that its deluxe tires average,
50,000.
no,
At least 50.
at least 50,000.
So it would be equal or less than.
Not,
I mean more than.
so my
50,000.
null hypothesis would be that the mu is greater than or equal to 5,000 miles, or 50,000 miles. Do I have enough zeros in there? That's my null hypothesis, which means my alternative hypothesis is what?
Equal to that it's not.
Nope, close. Is this a directional test or a non-directional test?
Directional. 'Cause
It's
all
directional.
Above.
Right. So they
equal
said,
to or above.
so their claim is what?
That
That
the
it's
mu
50,000
or
or
above.
more. It's
Right.
at least 50,000, right?
Yeah.
So they're saying it's 50,000 or
More.
more.
Okay.
So our
So we just have the
alternative
one sign.
hypothesis would be that the mu is,
More than 50,000.
no,
I mean,
Last
oh, less
Less
than
than.
50,000.
Less
Right.
than
That's what I meant to say.
50,000.
That 50,000 would be more.
Okay.
Right.
Now, see, if they're advertising that they get at least 50,000 miles, and we took a sample of 31 tires, and they only had 46,900. If that's if they're lying about their tires. It's misadvertisement, right? If I take 31, now the aspect behind it is we're going to look at this. So that means when I'm looking at I'm going to draw my table. And here they're saying that the mean is 50,000 top miles, right?
Mhm.
Well, we got a mean of was it 46,900?
Yeah.
Okay. We got a mean of 46,900. Well, depending, if this is too far below, then we can say, we don't think that the mean is actually 50,000. We think we just proven that it's lower. That's what we're gonna sort of look at. Because if we get I did 31 samples and the mean is less than $50,000, that's false advertising,
Right.
right?
Right.
And companies can get sued for that. So they have to sort of do that. So mathematically, is this really less than this?
Yes.
Well, we don't know, because remember, we would expect,
Oh, that's our hypothesis, but we don't.
see, this is our hypothesis,
Yeah.
is that it's 50,000. Our alternative hypothesis is that it's actually less than 50,000. So if it was too far down here in the tail, then we would sit there and say, with some degree of accuracy, that we're 95%, so we're not going to choose an alpha quite yet. But that's what we're sort of doing. So the farther this gets down here, the less likely it is to occur, right? The closer we are into here in the meat of the table, the more likely it's to occur. So when we start looking at it, that's what we want to do. Is it too far away from the mean? Is it more than 1 or 2 standard deviations from the mean? So that's what we're basically going to try to test and prove. If it's too far down here, if it's too far out here, we can reject the null hypothesis. Okay? So we have to go back, and we're looking at that. So my null hypothesis is greater than or equal to, which means my alternative hypothesis would be less than. And then the next question says, well, what is it that I'm actually testing, and what I'm actually measuring is what?
The average
The average
lifespan
in
miles.
miles. So X bar represents the average lifespan in miles. Now we determine, because the population standard deviation is known, we're using what distribution?
The normal.
The normal distribution. And when we look at the normal distribution, we look at 2 characteristics. What are the 2 characteristics that we put in here?
The P and
No, that's
that's
a
proportion. That's proportion. What do we put in
So
there?
this is a test of what? Means.
Yeah.
So the mean is going to go here. What did we speculate the mean
Oh, the
was?
standard deviation wasn't the other one. The mean.
The mean is, no, that was the one that we calculated. So we're
50,000?
actually going to use the 50,000.
Oh, yeah.
We use the mean of the hypothesis, not the mean of the test. And what goes here? No, that's where your mean of the mean of the means go. That's your standard error. So standard error is going to go here.
Okay, wait, the 50,000 is using the means of the what?
Huh?
Of the
When
population?
we're using the distribution that we're using, we use the distribution where we said the mean was
50,000.
50,000, and then we have to calculate what our standard error is.
I mean, but what did you say? It's like we use the means of the population, not the means of the sample? Like, we use the means of the...
Would you rather use an accurate number or an estimated number? So see, this is the whole idea. If we use it, we decided we were using the normal table, What's the formula for the standard error of the normal table?
The standard deviation divided by the square
The
root
standard
of the count.
deviation of what?
The population.
The population divided by the
The count.
square root of n.
Yeah.
So if I'm looking back here, which of these two standard deviations am I going to use? Am I going to use this or this?
The 8,000.
The 8,000, because it's the standard deviation of the population that is known. So to calculate my standard error, I'm going to take the 8,000 divided by the square root of 31. So that gives me a standard deviation of 1,436.84 miles.
So we only use the standard deviation of, we only use the sample one if we don't have the actual population one given.
Correct. If we don't know the actual population, we can't use it.
But if we had the population
It's
count,
it's
if-
better to use
yeah.
it because
Yeah.
it's more accurate.
yeah, so even if we just had one versus the other, we only had, say if we had not the accurate count, we just had the sample count, and then we had the actual standard deviation for the population, would we still put the
I don't
population?
quite understand your question.
Because I was thinking that there were some problems where they gave the count
Well,
of the
let's not
population.
worry about some other problem. We're worrying
Yeah.
about this problem.
No, just worried I'm going to get the other one and get it all wrong.
Okay?
Okay, so population if we have it, if not, use the sample.
If we know, that's when we use this normal table, and that's when we use, so our standard error here is, we're going to take the standard deviation. So in this particular case, I took the 8,000 divided by the square root of 31, which gave me 1436. So that's 1436. Point what? 84?
My, I think my standard error is wrong.
Or did you calculate it using your numbers or my numbers?
Well, it says to round to 2 decimal places, but, when I round to 2 decimal places, I'm off by 100. But it's alright. I got it's, yeah.
Okay,
Oh.
Now. this is the next question that we have to ask. We've got to calculate a
Mine is confusing.
test statistic. The test statistic is, since we are using the z distribution, we're going to use and here's where it really doesn't matter at this point. The test statistic is still going to be calculated the same way.
I think I got. Okay, so does SE is the standard deviation divided by the square root of the count
Standard deviation of what?
of the population.
Okay.
Which I did that, which is the 8,000 divided by the square root of 50,000.
No.
No,
Why 50,000?
the count, right?
The count. The count of what?
Oh, the tires.
The count of the number of people in the sample, not the mean of the.
Oh.
Now, the test statistic, in this particular case, my test statistic is what?
Z?
Z, because we use the Z table. Now, the way that we calculate the test statistic doesn't matter. It's the same for both. It's still the same. The calculation for the test statistic is still the same. The calculation for the test statistic And I am often going to label it this way. I don't care whether I call it Z or T, it's still the test statistic. I still calculate it the same way. The only difference is, it's going to be
1.64.
whatever my X value is minus the mean divided by the standard error. Now, if I use the Z, I'm going to use the standard error, which we just calculated. If I'm using the T-table, we use the estimated standard error, because we don't have the standard error. If we had the standard error, if we had the population mean, we would use the other one. So that's how I'm going to calculate that. So in this particular case, what is my X value? And sometimes they'll actually write this as my X bar minus the mean.
Would that be my mean?
It would be the mean of the, because remember X bar is the mean of the sample. So this would be, in this case, 46,900 minus the mean of the population, which was what we were testing against. It's always going to be the one that's in our hypothesis. So it's going to be 50,000. And the standard error, well, I have to go back because I had to calculate that. The standard error was what? 1436.842. So when I calculate this, does anybody? I'm going to go back to my Excel spreadsheet. So I'm going to come down here and I'm going to calculate the test statistic.
Statistics, here we go again.
So that's going to be equal. Now to do this in Excel, what do I have to do now?
Please tell me, I have no clue.
What did we just do? What did we write here?
Oh, okay, so I think I did it
The
right.
mean of the sample minus the
The 50,000.
mean divided by the standard error. But when I do this in Excel, I have to put this in, since it's the numerator, what do I have to make sure I do, Megan?
Parentheses.
Put it in parentheses.
Okay, so I did it wrong.
Okay, so I'm going to take this. Now, I'm going to take the mean of my sample, I'm just going to click on it, minus the mean of the 50,000. I didn't write that, but I'm going to put it right here on my null hypothesis. And then I'm going to divide by my standard error. And I had to go in and type that 50,000 in there. I typed it over here, but I don't have it in the cell by itself to calculate, right? So I just put it in this column over here. So when I do that, I get a test statistic of what? Negative 2.15751. So when I go back to my picture, if I actually was doing that, and now I'm going to make this look a little bit more realistic, because we just calculated it. This was my 46,900 which gave me a test statistic of what? Negative
157.
2.157. Now, my question is that far enough away to sit there and say, I reject the null hypothesis? And I can now, I have to come back, and there's two ways that we're going to decide whether this is far enough out in the tail to reject the null hypothesis. Okay, so we calculated the test statistic, which was what? Negative 2 point. Negative 2.16, did it say 2 decimal places, 3 decimal places. So negative 2.158. Now, here's the one place where I do this a little bit different than the book does. I'm going to show you both ways to do it. I tend to use table values. So I'm going to look at this, and to do the table value, okay.
It's worth 593 points.
Yep.
Okay.
Wow.
So if I'm looking at this picture, there's a couple ways of looking at it. Which one of these 4 pictures would this graph be actually doing?
It would be the second top one.
The second top one. Remember, I already drew it, it's right here, right? So it's actually the second top one. So now what we have to do is decide whether or not. Now, they talk about a p-value. The way that we get the p-value is we just calculated this number. I can go to my z table and look